In June 2025, the world watched hundreds of missiles crossing the night sky, creating luminous trails visible from miles away. The conflict between Iran and Israel showed the world one of the most impressive technologies of modern engineering: ballistic missiles. How is it possible to launch a projectile and hit a specific target thousands of miles away? How do these machines manage to travel faster than anything created by man? Today, we will explore the engineering behind ballistic missiles. Before we start, please leave in the comments your name and the city where you are watching our content. Ballistic missiles are basically gigantic and extremely sophisticated projectiles. Unlike airplanes that fly sustained by air, or missiles that keep engines running throughout the entire flight, ballistic missiles accelerate at the beginning and then follow a natural trajectory, like a thrown ball, only at incredible speeds. The big difference is in speed. While airplanes fly at about 621 miles per hour, ballistic missiles reach speeds exceeding 12,427 miles per hour. It's faster than any vehicle ever built by humanity. To better understand, imagine throwing a stone. It goes up, reaches a maximum point, and then comes down following a natural curve. Ballistic missiles do exactly this, but on a gigantic scale, rising up to space and coming down on the other side of the planet. This extreme speed brings advantages and disadvantages. The advantage is that they are almost impossible to intercept due to speed. The disadvantage is that once launched, they follow a predictable trajectory, allowing defense systems to calculate where they will fall. The name ballistic comes exactly from this characteristic. They follow the same physical laws of any projectile, only applied on a much larger scale and with much more advanced technology. The engines that propel ballistic missiles are among the most powerful ever created. In just a few minutes, they need to accelerate several tons to speeds that exceed the speed of sound by more than 20 times. There are two main approaches. Solid fuel engines are like giant fireworks. Once lit, they burn until the fuel runs out. They are simple and reliable, but cannot be controlled after being turned on. Solid fuel works like a chemical mixture that burns in a controlled way. Imagine a giant candle that burns with enough force to push a building. That's the scale of energy involved. Liquid fuel engines mix two liquids that explode when they meet, generating controllable thrust. They allow greater precision, but are more complex and can fail more easily. The advantage of liquid fuels is that they can be turned on and off during flight. This allows trajectory corrections and finer control over exactly where the missile will hit. The choice between the two types depends on specific needs. Missiles that need maximum reliability prefer solid fuel. Missiles that need greater precision use liquid fuel. Many modern missiles use multiple stages, where different sections separate during flight. Each stage has its own engine optimized for different phases of the trajectory. One of the most impressive aspects of modern ballistic missiles is their precision. They can hit specific targets after flights of thousands of miles, something that would have been impossible just a few decades ago. Navigation works through systems that track every movement of the missile from launch. Extremely precise sensors detect any change in direction or speed, allowing onboard computers to know exactly where the missile is every second. Imagine trying to hit a target the size of a football field after throwing something from one city to another. That's the scale of precision these systems can achieve. During the launch phase, small engines can make corrections to the trajectory. Once the main fuel runs out, there's no way to correct the path anymore. That's why initial precision is fundamental. Modern navigation systems are like extremely advanced GPS. They know exactly where they are on the planet at every moment, even traveling at extreme speeds. Modern systems can also use satellite signals to verify position, but need to function even when these signals are blocked. Navigation must be completely independent to work in conflict scenarios. The challenge is that small errors at the beginning become big errors at the end. A deviation of just 1 degree can make the missile miss the target by miles after a long flight. When ballistic missiles return to the atmosphere, they face one of the greatest challenges in engineering: the heat generated by extreme speed. Speeds exceeding 12,427 miles per hour create temperatures that melt most materials. To understand the scale of the problem, imagine a spacecraft returning to Earth. Ballistic missiles re-enter much faster than any spacecraft, facing even more extreme conditions. The solution is to use special materials that sacrifice themselves to protect the payload. Outer layers literally disintegrate during re-entry, absorbing heat and protecting what's inside. It's like having armor that melts to save what it's protecting. These materials are designed to disintegrate in a controlled way, carrying the deadly heat away from the warhead. The shape is also crucial. Pointed shapes direct heat away from important parts, while ultra-resistant materials keep the structure intact even at temperatures that melt common metals. During re-entry, the air around the missile becomes so hot that it glows like a star. It's this glow that creates the luminous trails we see crossing the sky in the news. This is one of the reasons why developing ballistic missiles is so complex. Few materials in the world can survive these extreme conditions. Intercepting ballistic missiles is considered one of the most difficult challenges in military engineering. It's like trying to hit a bullet with another bullet, where both travel at extreme speeds. The main problem is time. Ballistic missiles are detected only during launch and re-entry. During flight in space, they are practically invisible to ground radars. Imagine trying to hit a car passing on the road, but you can only see it when it's leaving the garage and arriving at the destination. That's the difficulty of detecting ballistic missiles during most of their flight. Defense systems need to calculate exactly where the missile will be in the future and launch interceptors that arrive at the same place at the same time. Any calculation error of fractions of a second results in total failure. The extreme speed makes everything more difficult. While an airplane has minutes to be intercepted, a ballistic missile in re-entry may have only seconds before hitting the target. There are two approaches: intercept in space, where there's more time but no atmosphere for maneuvers, or intercept in the atmosphere, where there's less time but greater maneuvering capacity. Both require extremely advanced technology. The interceptors need to be even faster and more precise than the missiles they're trying to destroy. It's literally a technological race between attack and defense systems. Often, the strategy is to use multiple interceptors against a single attacking missile. This increases the chances of success, but also multiplies costs exponentially. Ballistic missiles are among the most expensive and complex engineering projects ever developed. A single missile can cost tens of millions of dollars, and complete systems cost billions. To put it in perspective, an advanced ballistic missile can cost more than a modern fighter jet. And unlike an airplane, which can be used thousands of times, a missile is used only once. The complexity comes from the need for everything to work perfectly on the first try. There's no second chance. Either the missile works perfectly or it fails completely. Each component needs to be manufactured with extremely tight tolerances. A poorly made screw can cause the failure of a billion-dollar project. That's why quality control is extremely rigorous. That's why only a few nations in the world can develop this technology. It requires decades of development, massive investment, and extremely advanced technical knowledge. The supply chain is global and highly specialized. Rare materials come from unique suppliers, and any interruption can delay projects for years. Each component needs to be exhaustively tested, but ironically, the final test can only be done by actually launching the missile. This makes development even more expensive and time-consuming. Training teams is also extremely expensive. Engineers and technicians need years of specialized training to work with this technology. The next generation of ballistic missiles promises even more impressive capabilities. Artificial intelligence may allow missiles to adapt their missions during flight, responding to changes in conditions. Imagine missiles that can change targets during flight, or that can identify if the original target still exists. This flexibility would be revolutionary in military technology. New materials can make missiles lighter and more resistant. Materials that are experimental today can revolutionize both propulsion and thermal protection. Researchers work on materials that are more resistant than anything available today. These advances can make missiles faster, more precise, and harder to intercept. More efficient propulsion can increase ranges or reduce costs. Engines that work differently from current ones can make missiles more precise or harder to intercept. Some experimental technologies promise even greater speeds than current ones. Future missiles may be so fast that they become practically impossible to intercept. Navigation also evolves constantly. Systems that don't depend on satellites can make missiles immune to electronic interference. Emerging technologies include quantum communication, which would be impossible to intercept or block. Future missiles may have completely secure communication with their command centers. Many technologies we use daily originated from ballistic missile development. Car and cell phone navigation systems evolved from military systems. The GPS we use every day was originally developed to guide missiles and other military equipment. Today we navigate the city using technology that started as a military project. Heat-resistant materials found application in civil aviation engines. Precision manufacturing techniques developed for missiles now produce electronics and medical equipment. Modern computers owe much to military research. The need to process information quickly in missiles drove the development of faster and more efficient processors. Even the internet has origins in military research. Investment in military technology frequently generates civilian benefits decades later. Composite materials used in sports cars and commercial aircraft were first developed for military applications. The search for lighter and more resistant materials benefits all society. Extremely rigorous quality control techniques developed for missiles are now used in hospitals and electronics factories. Military reliability standards elevated the quality of civilian products. Despite all advances, ballistic missiles still face fundamental limitations. The speed of light imposes limits on communication and data processing. Once launched, they follow predictable trajectories that can be calculated by defense systems. This vulnerability is inherent to the physics of ballistic missiles. Costs remain enormous, limiting how many can be produced. Manufacturing complexity means few countries can completely master this technology. Ballistic missiles represent human engineering operating at the limit of what is physically possible. Combining extreme speeds with metric precision requires technologies that are at the frontier of scientific knowledge. Each modern ballistic missile is the result of decades of development and billions in investment. It's technology that works at extremes, temperatures that melt metals, speeds that exceed any vehicle, precision that rivals surgeries. For engineers, ballistic missiles show how extreme limitations generate extraordinary innovations. When components need to work perfectly after conditions that destroy common materials, conventional solutions don't work. The technology continues evolving, constantly pushing the limits of what we consider possible. Each new development opens possibilities that before seemed like science fiction. In the end, ballistic missiles answer a fundamental question: how far can we go when we apply all our engineering capacity to a single objective? The answer continues to surprise.